Welcome everyone to our lecture number 6, where we're going to be covering work and energy, but under kinetics, right? So this is going to be our topic that we are going to cover. Mostly I share things that are more on the surface, but there's more work if all of us can try to get Hibla, the book called Hibla. It has all the work and examples that I use. So please endeavor to look for that book and use it. Of course, we have a lot of resources online that we can use and try to help us. All right, so we are going to look at kinetics of a particle. Under this, we are looking at work and energy. So the objective of this study is, first of all, to develop the principles of work and energy and apply it to solve problems that involve force, velocity, as well as a displacement. Another objective is to study the problems that involve power and efficiency, as well as the other objective, which is going to be our third objective, is to introduce the concept of conservative force and apply the theorem of conservation of energy to solve kinetic problems. All right, so let's dive into this work. Now, first, let's look at the work of a force. We know that every time a force is applied onto an object, this either causes displacement of this object, that means it moves from one position to another. So as it moves from one position to another, we believe that work is being done. And the way we represent work is normally represented by either W or U. W to represent work or U to represent work. Those are the symbols that we normally use. So now let's look at what we have here. So now a force, let's consider a force, which is F, being applied onto a particle right here, which particle describes a position, which is S. So now a force F will do work on a particle only when the particle undergoes displacement in the direction of the force. For example, so if the force F in this figure causes the particle to move along this path, which is S, right? Moving from position R here to position R prime, right? So that means that the change from R, right, from the displacement, which is R prime minus R, is what we have as our dr. But now you see, when you read this dr, if we try to represent the r on S, it means that is the S, because that's the position change of this particle, right? But now when we try to describe that in relation to force, now this dr is we try to it will be ds cos theta. Why? Because we are trying to put it on the position which is in line with the path being described, right? So now we know that the displacement is the r, right, which is r prime minus r, and the magnitude dr is the s, right? So that means that for us now to find the work done, that means that the force has displaced this particle from one position, which is r to r prime, then that work done, which will represent work as u in this case. So that means that now if we're considering a small change, so we have du, right? So our du will be given by F, which is our force, which is causing a displacement, then ds cos theta. That means that when we try to resolve this force onto I beg your pardon, if we try to resolve this s into dr, then we are going to have ds cos theta. So meaning that our du, right, in this case, our du or the cos would have been du being given by force times the distance that is displaced, which is the displacement, right? Because work is force times distance, right? So now we have force times dr. That means that this would be, but in terms of position as described, then we have to resolve, meaning that our dr is the same as the s cos theta. right? So remember, those are things that we need to take into account. All right, let's get back to learn more of this. So now let's look at work of a variable force, right? Let's look at work of a variable force. So now, if the particle acted on by the force F now undergoes what we call a finite displacement along its path, let's say from R1, okay, let's say from R1 to R2, right, which represents the position moved along that path S, which is from S1 to S2, right, then the work of the force is determined by integration because it's a finite element, right? It's a variable. So now the work done will be provided by or will be gotten by integration, right? Provided by integration of F, and the angle theta can be expressed as a function. So this is what we have. So we have a force varying, which is our force in this direction at an angle theta. That means that we can dissolve the force and we have our force cos theta in the direction of S. So that means that if we draw, we try to represent this on a force to distance drawing, realize that we are taking a small element right here, right? Which is which describe a displacement, which is a small displacement, ds, and this is the force that is causing the displacement, which is F cos theta, right? And it's moving from S1, right, from this point to S2. Then we need to find the expression, right? We need to find the expression of our varying force, right? So realize that for us now to find the work described by this varying force will be given by integration, and that one will be given by now U to represent work from position or S1 on the S path to S2 or position 2 will be given by the integration, right, of this force, which is varying with respect to the displacement, which is the R, right? Which is R1 to R2. But in terms of this, the path being described or the position, then means that we need to resolve the R, right? Which we saw that our dr was the same as cos theta. Oh, I mean, the same as the S cos theta. So that means that is this same thing is the same as integrating force the cos theta ds from position S, right, to position S1 to position S2, right? So those are our equations. Please take note of them. All right. So let's continue. Let's continue and then look at work of a constant force moving along a straight line. So we may have a constant force and it is pulling, like in the previous example we saw in 5, right? In lecture 5. So this is almost the same, right? Where we saw a plate being pulled by a constant force, right? So now we have work of a constant force moving along a straight line. So how do we determine the work done by that force? So here, let's take an example. We have a constant force, which is Fc right here, pulling at an angle theta, moving this particle from S1 to S2 right here. So that means if we resolve this force, we shall have the horizontal component on a straight line, which is Fc cos theta, right? So now if we try to represent this on a force to distance a diagram, realize that the force is constant, which is F cos theta right here. And then it moves this work, particle from S1 to S2, right? And then the work done is all what is shaded right here. So this describes the work done by that force to move this particle from position 1 to position 2. But now if we want to do it mathematically, how do we do it? So mathematically we said we integrate, right? So it will be U to represent the work done from position 1 to position 2 is the same as force, which this horizontal force, which is F c cos theta, right? And we are integrating from S1 to S2. Remember, work done is force times distance. So now we are now getting the distance, which is the small change, which is ds, moving from S1 to S2. So if we have an equation, for example, if I have an equation for this, then we can easily find that. So from this, we can easily integrate, right? Which is f cos theta from d theta from S1 to S2, you realize that when we integrate, we are going to have f cos theta, right? S2 minus S1, because the intervals are defined, right? When you integrate that, this is what we have, right? This is what we have. So now that is what we've gotten, and I believe now that is very simple for most of us, okay? All right, let's look at now work of a weight, right? Remember, weight acts towards the gravitational force. So now, if we consider a 3D body, right? We consider 3D body or a 3D particle, 3 dimension. So realize that it will have a dimension in the X, Y, and Z, or I, J, K vectors. So now you realize that really this component will have weight in those direction of X, Y, and Z. But in other cases, you realize that there's no weight in the X, there's no weight in the Z, and the only weight is in the Y direction, because this is acting towards a gravitational force. So now consider a particle of weight W, which moves up along the path S as shown below, from position S1 to position S2 at any point. So the displacement, that is our small change dr, right, now would be given by would be given by the r, which, because now it is a 3D dimension, right, would be given by dx in the I direction, plus dy in the j direction, plus dz or in the k direction if you are considering vectors. But remember, our work, our weight acts downwards, right? So we have, now we're going to have energy, because the energy is going down. I mean, the force is moving down. So we shall take that as negative. So we look at this as being integrated in both directions, the x, y, and z, but realize that x is 0 and also z is 0. So we just remain with y, because it is in the y direction. So we realize that our energy, or sorry, it's not energy, I beg your pardon, the work done, which is u, would be given by the integral of from moving from y1 to y2 of weight to w, right, dy, moving in the distance of y. And you realize that our weight is negative because it's moving down, and negative means it's moving down, and moving from position y2 to position y1. So this would be our equation describing the work done, which is from one position to another, being given by negative y, given by the change in y, right? So that will be describing this very thing that I've been speaking about is being described in this figure right there, right? So I hope that is clear for all of us. Right. So now let's look at work over spring force, right? Let's look at work over spring force. So now remember, for spring force, remember our force was we get an equation from previously. Those who have done chapter 5, sorry, lecture 5, you know how we're coming up with force and the case to represent uh, the constant force within that spring, right? So now let's look at work of a spring force, right? So now we look at the spring constant, right? So our work done, we said, is represented by U, is given by the force, which, right, times the distance, right? But remember, for spring, force is represented by the constant, spring constant, and then the distance moved, right? By then ds, right? So we are going to now get those what we need. So now let's consider the position at s is equal to 0, right? Then this particle having a force constant k, And this is the force Fs, which is the force on a particle, right? So now for us to get the work done, we are going to integrate the distance, these moves, which will be the work done from position S1, position S2, be given by the force of the particle times the distance moved, which will be given by this expression, which we already got in our lecture number 5, and then with respect to S. So that means that our spring will be given by a half, right? If we integrate, will be given by a half k s squared s position 2 minus a half k and position squared of 1. So now we're scaling the position because S was the position. Because remember, for it to get the force will be given by the force constant times the distance it covers, right? So now this is why we have the distance squared for this. So that means that if we represent on the graph right here of force against distance covered or position, this is how it's going to be described. This is the equation describing the line, or in describing the motion being moved by the force. And this is the work that is being done by this force. So the work is negative since force acts in the opposite direction, right? Because this spring opposes this, as the force acts this side, so the work is negative because the force is acting in the opposite direction. Therefore, the work is negative. All right. Let's continue, right? Let's continue. Let's look at this example. This example, because I've explained about the case. So what I'm going to do is, because now remember the force is inclined at some point. We have a particle that is inclined at some point. So guys, I'm going to give you this example, and you're going to try it out together with the exercise, and it will be handed in. So this example, it is for us to try it out, because I've just given you all the principles. So all you need is to apply the principles and solve it. But I've given you the answers right here. Okay. Now, the 10 kilogram block shown in figure, this figure right here, rests on a smooth incline. If the spring is originally stretched 0.5 meters. So determine the total work done by all the forces acting on the block when a horizontal force P of 400 newtons pushes the block up the planes. S is equal to 2 meters. These members, let's try to work out this. And also, I have this very example in Hebrew, so we can all try it out, right? And make sure that your answer that you get is equivalent to this, okay? All right, let's continue to more principles. Of course, I'm also going to send some videos for you guys to understand this principle more. Right, so let's look at the principle of work and energy, right? So now we're looking at energy as well as work. There is principle of conservation of energy that we are going to see later on. But let's also look at energy, right? Remember, when a particle is moving, first of all, from one position to another, it has initial velocity. That means that there is energy done, whereby now the initial velocity done, we're going to look at it in terms of kinetic energy. Remember kinetic energy? With this time, we are going to represent kinetic energy with T, right? Whereby kinetic energy, we said, is the same as a half mv squared, right? Remember, that is a half mv squared. So kinetic energy is a scalar, right? It's a scalar. That means that it does not have a direction, right? So that means that it is a scalar, right? Scalar quantity, right? It's not a vector, but it's a scalar quantity. So now if you have a particle, right? Let's say we have a particle and it moves from rest, that means that the kinetic energy, the velocity is 0, right? And then moreover, if this particle moves from one point to another, that means that the particle has made some work, right? There's a relationship. And then if this particle stops or increases in velocity because of the forces being pulling it, then there's a final velocity, right? Which we know as the final velocity, which final velocity will give us another kinetic energy, which is also given by half mv squared by v. This time will be the final velocity. Okay, I hope I'm clear. This is where we are going. These are some of the things that we are going to be looking at. Okay, let me dive into this, the principle of work and energy. So consider the particle in the figure below, which is located on the path defined relative to an initial coordinate system, right? So let's look at this particle right here, and it's moving initially from position 1 to position right here, position 2, and then there's forces that are summing up or causing the motion. And now let's say the Fr, which is the resultant force. So the resultant force is the summation of all the forces, right? In whatever direction it's going, right? So it's the resultant of all the external forces that are acting on this particle. So now summation summation of F, which is now given by, now the one that is the body is acting on, is given by the mass times acceleration. Remember, in the previous lecture, we said that force is the same as ma, which is the mass times its acceleration. This is the equation of motion for the particle in the tangential direction. So now in this direction right here, that means that in this direction, or which we have summation of F1, the body is moving with an acceleration. And that acceleration, will give us that force as a F being equal to ma, right? ma. But a is the acceleration that the particle has gained due to its motion, right? But remember, from our first, so that's our second lecture and second or third, we say that AT, or which is acceleration at any given time, is given by the change by V dV, then over ds, right? So that means that we can use this equation, integrate it, and in case of this position, and then we are able to determine the acceleration at any given time. Or perhaps we can use our other equation where V is the same as V naught, right, plus AT, A times time. So from there, whatever we are given, we can find that. Or other equation where we can include the displacement, and then we're able to find the acceleration at any given time, right? Perfect. So now, this is now summing up our now work done. So now summation of work done will be given by from S1 to S2 of Fi ds, which is the same as mv, right? From V1 to V2 dv. Also, this is F1, because remember I told you F1 is now having acceleration, which acceleration now is having kinetic energy, which kinetic energy is a half mv squared, right? So remember, now we are bringing in the acceleration, whereby v is the final velocity at position 2, whereas v1 is velocity at velocity 1. That means that the work done will be given by the change in the kinetic energy within these two positions. So that means that the work done by the force will be given by the change in kinetic energy, right? I hope that is very clear for all of us. Please take note of that, right? So let's continue. So now, remember, I'm going to explain this. Guys, remember, if you have a particle, let me get my pen right here. Remember, if you have a particle right here, started from a position 0, okay, let's call it this S1, right? And then it's moving with S2, right? And they say at this point it had velocity 1, and at this point it has velocity 2. But as it moves from this point to this point, it has what we call work done. We shall call this work done as U. Okay? We have the work done here as U. So that means that at this point, it has kinetic energy, which is T1, right? So if we also sum up the work done at this point, from move this particle from S1 to S2, that's what we call summation of U from 1 point to point 2 again. But this now is the same as the total kinetic energy, or it's the same as the kinetic energy at position 2. Right? So if we add up all this work, the work and the energy would equal to the final kinetic energy, right? Right? Okay, please make sure you know that. So this is what we are trying to explain. So the principle, that's what I will call the principle of conservation, right? Okay, the principle of work and energy is that the particle's initial kinetic energy plus the work done by all the forces acting on the particle as it moves from its initial to its final position is equal to the particle's final kinetic energy. So that's what I've just explained right there. Okay, so we need to know that, and that is very much important in our calculations, as long as forces acting on a particle and motion and velocity and acceleration and displacement is involved. Okay, so now let's look at a scenario. So a car collision buffer system made of hard rubber spring is to be built. You are required to predict the elastic modulus E of the rubber to be used. If the springs have cross-sectional area A, right, natural length I, and safety of contraction C, and the cars are each of mass M, velocity V, and are to be decelerated to rest. Okay, this would work, this scenario would work actually if we had covered some of these things in material science. But anyway, because some of these things we have not covered, like elastic modulus and all that, you guys may not know this, so probably I'll skip this and just continue with the work, right? Okay, so work, let's look at work of friction caused by sliding, right? So now let's look at work of friction caused by sliding. So now we know that if the surface is rough and there's motion or being put on a particle, then there's going to be an opposing force opposite in the direction to where the force is being applied, and that's what we call the friction force, right? So if the applied force, now let's say P, just balances the resultant frictional force, which remember when we are getting frictional force is the same as the normal force, and this time could be the weight times the coefficient of friction, which is nu K, then due to equilibrium, right, due to equilibrium, this is what we call the friction force, then due to equilibrium, a constant velocity, V, right, is maintained. And remember from our principle that we've just seen previously, we know that summation of the initial kinetic energy right here, plus the work done, now this is the work going to be done by friction force, right, is the same as the final kinetic energy. So now this is V1 and this is V2, but now the work done here initially is going to be work done due to friction, right? Okay, now let's go back and try to do this. So now this is what we are trying to say. That's a half mv squared, which is, this is V1 in this case, plus the work done by the force, which is going to be, this force is going to move into a distance s, which is P, s minus, now if we have the friction, which is opposite in this direction, right? It is opposing, right, the flow of this particle, right? It's opposing the flow of motion of this particle. That means that it is in the opposite direction right here. So that means that this is the friction force, which we get as nu K, or the coefficient of friction times the force, and that's friction, then times the distance covered, which is S, right? So now this is the same as a half mv squared, but this is velocity 2. But remember, velocity is constant. Also, remember, if the velocity is constant, if it's maintained at a constant, then that means this cancels, and therefore that means that PS is the same as in UK NS, right? So that means P is the same as that. So that's how we can try to solve other things if they're unknown. But let me dive into what I'm teaching, okay? So now, I think let's look at an example right here, which we are all going to still, I'm going to give this as another still assignment because I told you guys to look for Hibla, and Hibla, you're going to, I think also I'm going to share it on Google so that all of us have that book and we can truly try to use it to understand some of these things. Right, now let's look at this example. I'm going to leave this example for you guys. We are going to use this principle and then we are able to calculate what is required or the distance s. So now look at this, a 3,500 pound automobile shown in this figure, right, travels down the 10-degree inclined road at a speed of 20 feet per second. If the driver jumps on the brakes, right, causing the wheel to lock, determine how far, that means the distance s, the tires skid on the road, right? The coefficient of kinetic friction between the wheels and the road is this, right? So now we have the force, which is 3,500 pounds, and then inclined at an angle which is 10 degrees, and then they want you to find the distance by which this person applies the tires and then skids, the tire skids. So now we are going to use the principle above here, which is a half mv squared plus this plus that is equal to that. You know the final velocity, and then we know all this, and then we can easily find the answer. So please, I want this in your revision as we study today. I want you guys to come up with this answer as well as submit it in our assignment chat. All right. All right. As well as I think this one, as well as this other one, this second example, you're also going to work it out. Of course, these examples are in Hebrew, and I want you guys to try out because these are just simple examples and I'm not going to go through them. So now this other example is the 40-kilogram boy in this figure, right? Slides down the smooth water slide, right? If he starts from rest at A at this point, right? Determine his speed when he reaches B, right? And normal reaction, right? The slide exerts on the boy at this position. Also, I'm going to send accompanying videos that are going to help you understand these examples and be able to solve them. Okay, so this is another example I want you guys to try out. I'm not going to show it to you. You're going to try it out. And these are the answers that I've given you. Okay. Also, this is going to be another, after solving this example, you're going to try out this trial question, right? It's also going to be yours this time because I'm going to give you the book for you to look at how these are solved. Reason why I'm doing this is that most of you guys have really were really lazy on the test that I gave. Some of you really didn't know what they are doing, so it's surprising me. That's why I'm now going to tighten the knot so that members can pull up. All right, good. So now you try out also, this is your trial questions. So those are now 4 questions I've so far given. Please make sure that you work them out. Okay, so let's look at conservative forces and potential energy. So if the work of the force is independent of the path and depends on any of the forces' initial and final position on the path. Then we classify this force as conservative force. Okay. So now let's look at examples of conservative forces. We have a weight of a body, right? Because it goes hand in hand with the gravitational force, and the force developed by a spring, right? The force developed by a spring. Remember, force developed by a spring, that force F is given by Ks, the constant of the spring determines the distance that it moves. So now let's define energy. So energy is defined as the capacity to do work or the ability to do work, right? That is energy. For example, if a particle is originally at rest, then the principle of work and energy states. Now, if it's at rest, that means that our T1 is equal to 0 because the initial velocity V1 is 0. So that means that from the equation up there we have just seen, we have that since T1 is 0, then we have summation of the energy from position 1 to position 2 is the same as the final kinetic energy. In other words, kinetic energy is the same as work done to bring it from state of rest to velocity, right? Okay, hope that is very clear. Now, let's continue. So now, let's look at gravitational potential energy, okay? Remember, potential energy is given by mgh from your physics, mass, gravitation, gravity, acceleration to gravity, times the change in height, yeah? Right? So now, this is the same principle we are going to apply right here. So now, gravitational potential energy, if the particle is located at a distance, let's call it y, right? And above an arbitrary datum. So now this, if we have a datum right here, so this is very much important in when you're dealing with problems that involve pulleys and all that. Okay. Anyway, so if we have a datum and then we have a height of this particle right here, so let's call it y, or perhaps above the particle. If it is below, then it is negative. So particle's weight, which our weight is here w, has positive gravitational potential because potential energy will be given by mgh. Okay, this time our h is y. So likewise, if the particle is located at a distance y below the datum, then the gravitational potential energy, which we call it a Vg, is negative since the weight does negative work when the particle is moved up back to the datum, right? At the datum, at the beginning point, there is no gravitational potential energy, so it is 0. So that means that gravitational potential energy, this time we are representing Vg to represent gravitational potential energy given by the weight times the vertical distance it covers, right? Okay, so I hope that is very clear. Perfect. So now, let's look at elastic potential energy, right, for the spring. So when an elastic spring is elongated or compressed for a distance s from its unstretched position, elastic potential energy, which we are going to call it as VE to represent elastic potential energy right here, can be stored in the spring. So the energy in this time, because it is stored, is going to be positive and it's going to be given by a half Ks squared, right? It's a half Ks. We say that, remember, from there, remember we had said F somewhere was given by the integral, right, of K, right, of S from position S1 to position S2, right? Remember, we did those kind of things from our previous work. All right. Okay. So here V is also positive since the deformed position, and then the force of the spring has the capacity or the potential always of doing work on the particle when the spring is returned to its unstretched position. Okay, so now let's continue. So this is unstretched position, which is S is equal to 0. So that means that this is a switched position. But now, if this particle pulls its position to this side as it goes, that means that the work is positive. Remember, last in the one of the slides above, we saw when the force was going this side, and that work is negative. Okay, but now let's just take what we have here, that the work is positive. So that means that if this returns to unstretched position, that means that the work stored is the same as the elastic potential energy, which is given by a half Ks squared. Perfect. Now, let's continue. Let's continue. Look at the potential function. So now, if in the general case, if a particle is subjected now to both gravitational and elastic, and let's say it has a spring or elastic forces, then the particle's potential energy can be expressed as the summation or as a potential function, which is the algebraic sum, right? Which is given by the summation of V, which is the potential given by the summation, which is the gravitational potential plus the elastic potential. Okay, right. Okay, so we are going to see more examples even in our tutorials later on. So now let's dive into conservation of energy. Okay, let's look at into conservation of energy. So portion of the work done by conservative forces on a particle can be written in terms of potential energy difference, right? So we say that if the energy, we remember we say T1 minus T2. So now this is now the potential energy. We have V1, V to represent potential energy. So that means that the potential energy at starting position, when as potential energy at the final position, right? This is what we have right here, is equal to the work done, right? Is equal to the work done. So by principle of work and energy, so that means that T1 plus V1 plus this non-constant work done is the same as T2, which is the final kinetic energy plus the potential energy. So this means that the initial kinetic energy plus the initial potential energy plus the work done is the same as the final kinetic energy plus the final potential energy. So if only conservative forces do work, now if only conservative forces do work, then that means that the T1, right, plus V1, right, is the same as T2 plus V2 because this whole thing will go to 0, right? So this conservation of mechanical, this is conservation of mechanical energy equation, okay? So we have to note that this is the conservation of the mechanical energy equation. Okay, right. So let's continue to make us, let's look at the statement. So during the motion, the sum of the particles' kinetic and potential energy remains constant. That is the statement, right? So that means that kinetic energy is conserved, right? So that may also brings us to the principle of energy. Energy cannot be what? Created or not lost, right? Remember that the principle. Anyway, you guys know it. Consider a ball of weight W dropped from a height which is h above the ground or the datum, the starting point. So we are now looking at how the potential energy, how energy changes. So the particle moves with the potential energy, which is maximum at this point because the height is maximum. Okay. If we have a datum, this is a starting point. So at this point, the potential energy is maximum. The kinetic energy is 0 because at this point, the body is at rest. So at this point where h is half, the potential energy, and this ball has both potential energy as well as kinetic energy. Whereas at this point 0, if we start from here, our height is 0, meaning potential energy is 0, whereas the velocity is maximum, so the kinetic energy is maximum. Okay. So you still remember those things in physics. This is what I'm trying to explain. So at maximum weight, HV1 is maximum and T1 is 0. So that's what I've been explaining. So total mechanical energy at that point, which is where H is max. So we have T1 plus V1 is equal to 0 plus the weight of the ball. So that means that the energy will be given by HWH, okay, which is the weight, which we call mgh, or which we call the weight, which is times the height. So at a half h, the speed of the ball is determined from v squared is equal to v naught squared plus 2dh, because we know acceleration due to gravity, and therefore, since we know that, we can determine the final velocity. Initial velocity is 0, so that means that our final velocity is given by twice the gravitational force over h over 2, so it is given by kh, right? And then we find the square root. So that means that from there, we can find our square root, as v is given by the square root of gh. Therefore, at mid, our energy, we have T2, right, which is the kinetic energy, plus the potential energy. But remember, at this point, the potential energy is given by a half of the distance, which will be the weight, right, times height, as well as our kinetic energy will be given by a half m mass, where my mass is the same as the weight divided by the acceleration due to gravity. Right here, this represents the equation, and then this is our velocity. So this means that it will be a half wh, right? So that will be our final equation. Okay, so this is what they're trying to define for us. I hope that is clear for everyone. So just before the ball strikes the ground, its potential energy is 0, and its velocity is given by 2gh, right, the square root. Hence, again, the total energy of the ball at that point will be given by E, which is T3 plus V3, which is a half mg, then find the square, plus the potential energy, which is 0, which is equal to WH. So that means this is the same as what we began with. So energy is conserved. All right. So now we are going to look at an example, which I want you guys to try out in your different groups. So please, guys, try out this. And I need to find that you guys have the same answer. Of course, I have these numbers explained in Hebrew. You can try out that, but I need also your input to try them out. Perfect. Okay, so this marks our lecture today. I'm going to send more videos for us to understand and get this concept into use. All right, so that marks our lecture 6. I hope everyone to put in time and study these things. Okay, all right. Thank you.